All right, welcome everybody to the 2020 Aspen Center for Physics Heinz Pagel Physics Talks, an online version of the series that's usually offered at the center in happier times. My name is Csaba Csáky. I'm a professor of physics at Cornell University and the general member of the Aspen Center of Physics. Next year I will serve as the scientific secretary here, and I will be doing the introduction today. If you did not receive an email of the lecture schedule or the description of tonight's lecture, these are available on our website at aspenphys.org. You can be added to our mailing list by contacting the center. This series of talks will be online every Thursday evening at 5:30 Aspen time through August and posted on YouTube the following day. For those of you who are not familiar with the Aspen Center for Physics, I would like to say a few words about the center itself. It's a truly unique institution, which is the envy of the physics world. During the summer, in normal years, it hosts about 500 of the leading physicists from around the world who come to Aspen to exchange ideas, generate new collaborations, and learn from each other. In the winter, it runs a conference series of about 10 conferences in different disciplines. The center is completely self-organized. There is no large university or national lab behind it. It is run by the volunteer work of the members and the very small but very amazing staff of only 3 people. We really hope that the center will be there for many future physics generations to take advantage of the unique opportunities it offers and the amazing natural beauty of the area. And of course, the great people of the city of Aspen who are amazingly even coming to our online series. And of course, we all wish we were there right now and be able to hike the Ute Trail every morning. And we really hope that we'll be back next summer. So after this, let me finally get to introducing our distinguished speaker tonight, who is Professor Lisa Randall from Harvard University. She's probably the best known and most preeminent particle theorist of our times. But just in case you don't know her, I will give you the highlights of her career. She got her PhD in 1987 from Harvard. Then she was a President's Fellow at UC Berkeley and a Junior Fellow back at Harvard. She had faculty appointments at MIT and Princeton before she joined the faculty at Harvard, where she's currently the Frank D. Baird Junior Professor of Science. She's a member of the National Academy of Sciences, Fellow of the AAAS, has won many prizes, including the 2019 Sakurai Prize of the American Physical Society, 2019 Oscar Klein Medal, numerous fellowships, Guggenheim, Simons, too numerous to really list all of them. Lisa is renowned for her proposal of warped extra dimensions in 1999 with Raman Sundram and is considered leading expert of most aspects of particle physics and cosmology. She's also the leading ambassador of particle physics. Her books, Warped Passages, Knocking on Heaven's Door, and Dark Matter and the Dinosaurs were all bestsellers, translated to more than 10 languages each. Last but not least, she is also well known for her former grad students. I happen to be one of them from her early days at MIT. We will not interrupt Lisa during her talk, so you will be muted, but raise your hand by clicking the hand at the bottom of your screen if you have a question, and I will call on you during the question and answer session. We will wrap up by 6:30. Would also like you to know that your video image may be included in the YouTube posting. If you don't wish to be seen, please turn your video off when you're asking a question. Finally, we are pleased that many physicists are attending tonight, but this is a public talk, so your technical questions should be saved for another occasion. After that, without further ado, Professor Lisa Randall on darkly charged dark matter. Lisa, please go ahead.
Hi, well, first of all, thank you, Csaba, for that really lovely introduction. That was very kind. And during these times, it's hard to remember these things happened. And I also want to say that it's very nice to be speaking to all of you, but it's also really strange. When I've given a lot of public lectures, but usually I give a public lecture, I can see the audience. I mean, it's true a few of you are showing up Brady Bunch style, but it's not really quite the same thing as being able to see the people there. So I hope
Lisa, I think you're muted.
Oh, that would be pretty bad, wouldn't it?
We can hear her.
No, she's not.
She's not. You're not muted.
Yeah, I'm muted.
Well, it wouldn't be a Zoom meeting without some discussion of what's going on with the Zoom. So, am I muted or not?
No, we can hear you well.
Okay. Okay, maybe some people just don't want to hear what I have to say. But it's just, I wish I could actually see you and meet all of you, but I hope that this will come across well. And it's always really strange giving these talks at Aspen in particular, because you really do have a wide variety of people who show up. Usually a good part of the audience is physicists, and so you want to be speaking to them a little bit too. So some of this talk, most of this talk will not be very technical. A few times I'll diverge into things that might be of interest to people really thinking about physics actively. But I don't know who's in the audience now. It's really strange, but I will try to tell you a little bit about dark matter. So with that, I'm going to tell you about some work that I and others have been doing. It's called Darkly Charged Dark Matter, and you'll see why as the talk goes on. But it has to do with, just to anticipate, it has to do with the idea that we really don't know what dark matter is. And if you don't know what dark matter is, even in the sense of what I mean by that, don't worry, you'll hear about it very soon. But we as particle physicists don't know what it is in the sense of we don't know its identity, in the sense of what are all its interactions, what is it actually made up of. And that's a question that many people at the center have been working on. And I know I said I was done with my intro, but I should also take a moment just to say how wonderful the Aspen Center for Physics is. And I wouldn't be doing this talk if it wasn't to help out an organization that I really, really admire. I really think it's unbelievable how well it's done. I mean, I describe it to my friends who've heard of the Aspen Institute as sort of the orphan cousin of the Aspen Institute. I mean, it is really important to support it, because it's not just about getting names together and getting talks together. It really, a lot of work goes on there. It's a really wonderful institution, and people work really hard to make it work. So I hope that you also think about supporting it, because it's really great, and this is a lot of work for everyone involved. And I'm giving up my last day of vacation. So there we go. So anyway, so with that, we're going to talk about dark matter. So just to remind you, okay, the host has asked me to start my video. Is that?
No, your video is on, Lisa. It's okay.
Okay, it's showing up.
I should just tell people that you have two windows, and you can see her in the second Lisa Randall window. So
yeah.
You just have to.
You don't actually need to see me, but I just figured I would keep it away from you. Okay. So just to remind you, and probably most of you who are showing up know this, but some of you might not. The matter that we really know about, the stuff that we're made up of, the stuff that we see when we look out the window, the stuff that our whole world that as we know it is made up is really primarily made up of atoms. But the universe itself only sees atoms as about 5% of the net energy. Most of the energy is in forms that we call dark. Dark is a terrible name because dark stuff absorbs light. And when we talk about dark matter and dark energy, we're talking about stuff that, as far as we know, doesn't interact with light at all. Transparent would be a better name. But it is dark, as we'll see, in the sense of it's a mystery what it is, and we'll talk about that. But the important thing to notice is twofold. The first one is that the energy, things we understand, the things that particle physicists traditionally study, is only about 5% of the energy of the universe. But the other thing is that it's actually a really fairly significant fraction. I mean, it's kind of remarkable that these other components that we really don't know what they are, dark matter and dark energy, are not that different in size. I mean, they're not a trillion times more or a trillion times less. They're, 5 times more or 15, just really small. It's really about the same. So it's kind of interesting that there isn't this big difference in the amount of energy in all these components, and they all exist today. The other thing is, just to explain very briefly, dark matter is stuff. It's stuff that it's a horrible definition I'm going to give you, but it's the best definition, which is it's stuff that interacts with gravity like matter. That is to say, dark matter and ordinary matter that we're familiar with have exactly the same interaction with gravity. So it clumps together the same way ordinary stuff would under gravity. And the reason I say that is to distinguish it from dark energy. Dark energy is a smooth component of energy spread throughout the universe, as far as we know, uniformly. And it's presumably been there forever. We don't know for sure. And that's something that doesn't clump. It's just spread throughout the universe. So although there's technically a larger fraction of energy in dark energy, there's a bit more to study right now for dark matter because it does clump together. And that means that you can actually look at the structure in dark matter. And ultimately what this talk will be about is why, by looking at structure of dark matter, we can actually perhaps learn something about its nature. Okay, now, okay, there we go. So when I say dark matter, what do I mean? This is what I said before. It's matter that interacts via gravity, like matter. But as far as we know, there's no other discernible interaction. It doesn't mean it doesn't have any interactions, but there's certainly no interaction other than gravity that we've observed. Now, a lot of people, especially the interested public, will say things like, well, are you sure that you didn't get Einstein's equations wrong? Are you sure this really exists? I want to just point out that it's really not surprising that these dark components should exist. There's no reason they shouldn't exist. I mean, the thing that to me is in fact more surprising is that the matter we're made up of is 5% of the energy of the universe. In principle, it could have been a lot smaller, and that wouldn't have been that surprising either. Why should the stuff there's a whole universe out there. Why should the stuff that we can detect and know about be such a big fraction? Also, saying that this exists is a lot less radical than saying that Einstein's equations are wrong. And as I'm going to also explain, there really is strong evidence that it really is dark matter, that it is stuff that acts like matter, and I'll explain that. And I just want to remind you that even though individually the particles are very, very weakly interacting, the reason we know about it is because there's so much dark matter. I just told you there's 5 times the energy in dark matter as ordinary matter. It could be that billions of dark matter particles are passing through you every second. You wouldn't even see them or know about it or feel them. But despite the fact that individually these particles could be very, very weakly interacting, there's so much of it that it gave shape to the universe, as we'll see. So why am I so confident that dark matter exists? Well, there's a whole history of learning about dark matter. But one of the first ways that dark matter was really established was by Ford and Rubin and others, who measured the rotation of stars in our galaxy. And they found that those stars were rotating faster than could be accounted for by the visible matter, indicating that we were missing something. There had to be the stars were moving so fast that unless there was something else pulling on them, it would never have, it wouldn't have stayed in the galaxy. So there should be some other matter. And similar to that is the idea that galaxy clusters, which are balanced states of galaxies, again, the velocities of galaxies were faster than they should be. And in fact, Franz Vicky was the first one to observe this and thought that there could be something called dark matter. He's actually responsible for the name. And there's something that I like called gravitational lensing, which has to do, and the reason I like it is because it really helps us sort of trace where the dark matter is. And I have a picture because it's a slightly more complicated idea, but it's not very complicated. So we're sitting on Earth, right? So we're at the Earth, and we're looking at some bright object, which is a bright object. It's labeled cleverly object. So there's a star there. Now that star emits light, but suppose there's something in between that could have normal matter, could have dark matter. The light is lensed. The light bends around that, and it bends in different directions depending on how it went around it. So we think light went in straight lines. So when we project back what the path is, we would think that there's a blurred out image or multiple images. It's lensed. So we don't see the thing directly, we see a lensed version of it. But this lensing is really important because it's saying that even though dark matter is dark, it affects the path of light, which helps us trace where dark matter is in the universe. Another thing that I think is really compelling evidence that it really is dark matter and not some modification of gravity is something that's called the bullet cluster. Remember I said a cluster is a bound state of galaxies. The bullet cluster looks like it was formed from the merging of different clusters. And what do clusters have in them? Well, they have stars, but they also have gas and dark matter. And what you see in these two different colors is the pink is gas. And because gas interacts when they try to pass through each other, the gas gets stuck in the middle. Whereas the blue, the outer bulbous regions, are dark matter, which just pass through. And this is exactly what you would expect if it was dark matter. It's very hard to modify the equations of gravity to give you something that looks like that. This is exactly how you would expect dark matter to act. Also, the distant supernovae that told us about the acceleration of expansion of the universe, ultimately leading to the discovery of dark energy, really only did that because they pinned down how much dark matter there is too. So we know it is finding dark energy, but it also was responsible. We also learn about dark matter from these measurements. Something that's been very, very valuable is the cosmic microwave background. The cosmic microwave background radiation is radiation left over from the time of the Big Bang. And there's a lot of structure in that radiation that has to do with how perturbations in the universe were formed. So perturbations, and basically, if you have perturbations, they get bigger where there's more matter, and they're a little bit less when radiation pushes it away. So using that, you can figure out how much normal matter there is relative to dark matter, which is where we get those fractions that I presented in the beginning, although they are consistent with other measurements. But another thing that's extremely powerful is just the very existence of galaxies on the scale of the Milky Way is indication that there's dark matter, because radiation would have blown away any structure that was small enough to form our galaxy. So we needed dark matter so that something could collapse, and then ordinary matter kind of came along for the ride. And finally, and this is something that we knew for a long time, given how big those perturbations are, the universe originally was just homogeneous and isotropic. Perturbations had to grow to form structure like the structure we see that's responsible for our very existence. In the lifetime of the universe, there would not have been enough time for structure to grow unless there was more matter than ordinary matter. So dark matter is essential for the existence of galaxies in the lifetime of the universe. So for all these reasons, we are fairly convinced that dark matter exists. And this is basically how new things are established. You measure in very different ways, but they all give you consistent answers. They all give you consistent answers for how much dark matter there is in the universe. So I would say that the existence of dark matter is not speculation. We know dark matter exists. We don't see it with our eyes, but we do observe its gravitational influences. And I emphasize, these were all gravitational influences from the dark matter. So we don't know about any other interactions, but just gravity itself, the fact that it pulls on stuff, was enough for us to figure out that dark matter had to exist. You can ask, where is it? And the answer is sort of everywhere. But because galaxies formed around dark matter, where dark matter structure was there, there's also light in some sense. In our galaxy, we have the Milky Way disk, but we have basically a spherical halo of dark matter as well. We're surrounded by dark matter. You can ask, why is the ordinary matter, the bright stuff, concentrated in the Milky Way disk? And that's interestingly enough because the other matter does interact with light. And so it can radiate. And because it can radiate, it can lose energy and collapse. And because of orbital angular momentum, it doesn't collapse into a circle, but it collapses into more or less a disk, which is the Milky Way disk. So as I said, people are mystified by dark matter. You know, people will sometimes, you talk about physics and people feel completely comfortable saying, oh, I don't understand that at all. I mean, dark matter is not that hard to understand. It's just stuff that doesn't interact with the way our matter interacts. And it's essential to the construction of our universe. I wrote a book called Dark Matter and the Dinosaurs, And I like making analogies to it. And I do think it's kind of interesting because dark matter really was the scaffolding on which everything was built. Yet we pay attention to like the bright stuff, the stars. But really, this was important for the construction of our world. So it's sort of the unsung hero of our universe. A lot of evidence is all consistent, and as I said, it's basically how any new phenomenon or thing is established. But we don't know what it is. What is it made up of? Now, it's possible we'll never know the answer to that question. And the reason we don't know the answer is precisely because it's dark. It's really not interacting a whole lot. So it's hard to pin it down. But we're trying. And what are the questions we want to answer? Well, is it made up of an elementary particle? If so, what is it? And what do we mean by what is that particle? What do we mean, what is its mass? What are its interactions? Is it a single particle or are there many particles? And the question we're going to get to later on is, even if it doesn't interact with our matter, can it be interacting with its own matter? And that's going to be an interesting question we'll come to later. So this is why we think about dark matter. It's actually a great topic for research because we know dark matter exists and there's many observations of its influence, but we don't know what it is. Okay. But how are we going to answer this question? As I said, the existence of dark matter isn't necessarily so mysterious, but how do you find out what it is? Well, basically we have to look under the lamppost. We have to find clues that tell us where to look. Now, in the case of dark matter, it's almost literally true that looking under the lamppost isn't such a bad idea, because as I said, structure forms by ordinary matter collapsing along with dark matter. So it's reasonable to think that where there's light, there's also some dark matter in many cases. But we're still trying to think about theoretical and observational clues for what we might find out about dark matter. And I am a model builder. We think about options. We want to characterize the possibilities. So we're trying to say, what could it be? But really what we're thinking about when we ask these questions are, how do you test these ideas? So when I tell you my models, I'm not telling you things that I know are true, or if I tell you other people's models, we don't know if any of them are right. Well, ideally, though, we want to know that we'll be able to tell whether or not they're right, to think of some ways to test it. And really, if you don't have models, you often miss possibilities that would have been there. It's really useful for it to characterize what are the signals that tell us some information. And that's what we do as model builders. But I'm not going to, I don't want you to go away and say, well, dark matter has its own charge. It's a possibility. And like I said, there's many models out there, and maybe they're all wrong. But we want to see what the possibilities are and consider their implications. So before I tell you about new stuff, I'm going to tell you about an old idea. I always find it amusing because when people will sometimes introduce me and say, I work on exotic models of dark matter. Although a lot of people thought about WIMPs, weakly interacting massive particles, they also are exotic in the sense that we have no idea whether it's right or not. The fact that a lot of people work on it doesn't make it correct. But it's many people's favorite candidate for a long time, for a couple of reasons. One is that theoretically, if there is dark matter that is connected basically to the Higgs boson that probably you've heard a public lecture about, connected to the weak interactions, it turns out that there's the right amount of energy in the universe to constitute dark matter. That didn't have to be the case. So that coincidence means maybe there's some connection to dark matter. If you have some sort of neutral particle that's stable, maybe that's a dark matter, and that could be part of an extension of the what we call the standard model. But the real reason we like it, of course, is if it's an extension of the standard model. It means there probably are some interactions other than just gravitational with ordinary matter. And that means you can look for them. So in other words, even though it doesn't have a big interaction with light, maybe it has a little bit of an interaction. And we can predict what it is in any particular model. And there's experiments out there. You probably just recently heard about the xenon experiment presenting some results. But there's experiments out there that are looking for dark matter. So when people tell you that we've been looking for dark matter for years and haven't found it, almost always what they really mean is we're looking for WIMPs. weakly interacting massive particles. And this is a picture that someone put together for my book, which I love, because it basically tells you in one slide the 3 different basic ideas of how to look for dark matter. The one that's in some sense most direct is literally called direct detection. And it's a way we were looking for dark matter for years. And it's the way we're continuing to look for dark matter. And the idea is to have big vats of something like water or other material, some inert atom, underground to protect you from cosmic rays. And basically make it big enough that even though dark matter has really small interactions, maybe you have enough of it that you can see some interactions. And these experiments are really, really impressive, not just because they're big and can see sensitive things, but because they have to reject all the radiation that can mimic the signal. Dark matter is very weakly interacting. Basically, if you touch the thing, it would swamp the signal from dark matter. You have to shield it from many different things and test that whatever you saw really was dark matter and not just some ambient radiation. There's 2 other ways that people have recently been thinking about looking for dark matter. Another is called indirect detection. And the idea is that maybe dark matter particles meet each other in the sky and produce something visible. So that even though you don't see the dark matter directly, maybe they annihilate with each other and turn into something visible. Now, there's lots of visible stuff out there, so you have to make something that you can distinguish from ordinary matter. So you're looking for antiparticles or special spectra of radiation that can distinguish it. And so far, there's been a lot of signals, but usually they, in the end of the day, boil down to the fact that we predicted the standard signals wrong. So we still haven't discovered dark matter that way. And the final way is looking at the Large Hadron Collider. If there is dark matter, we would see signals that would be different than if there were not dark matter, if it's at the right energy scale. But so far, all of these have come up empty-handed. We've come up empty-handed. We have not succeeded in finding WIMPs. People are still looking. It could be that we're just looking at the wrong parameter space. But in 10 years, basically, we're going to run through the basic possibilities for WIMPs. And if we come up empty-handed, what will we do? So we don't want to just think about one model. It's a model. We don't know if it's right. We want to think about different possibilities. And there's a number of possibilities for what dark matter can be, and I don't have time to tell you about most of them. Probably barely have time to tell you about my stuff. But I just want you to keep in mind that there are a number of options out there, and I'm not telling you about all of them. Okay. But so I'm going to ask a very radical question, which is, suppose there were no connections really to the standard model. So there's no interaction other than gravity with the standard stuff, the stuff that we make detectors out of. Is there any hope to learn more? Now that sounds like the answer is obviously no, because it's not interacting with us. How would we ever detect it? But what I'm going to tell you is that the answer is actually yes, we can learn more if there are interactions in the dark sector. And until relatively recently, this was not a very explored option. But the idea is to have self-interacting dark matter. Dark matter that interacts with itself, not with our matter, but with its own matter. So just the same way dark matter doesn't see our interactions, maybe our matter doesn't see dark matter interactions. And maybe dark matter is a much richer society than we've given it credit for. We just don't see it because we don't detect those forces. And one of the really radical possibilities is that it could even be darkly charged. There could be its own electromagnetic force, a long-range force under which dark matter is charged. And that's what we're going to think about now. So we're going to eventually see that this stuff can have pretty radical consequences, distinctive shapes of galaxies, and even, since the public lecture, I couldn't help but tell you a little bit about the comet strike at the end. So we'll get to that later. Okay. But basically, the insight is fairly basic, which is why should normal matter be the only type that's special, that has structure, that has interactions? You know, every time we, it's funny because the critical revolution was a long time ago, but we still like to be the center of the universe. Like, we don't even like the fact that we're not central to the matter of the universe. Then when we say, okay, there's dark matter, we say, well, it's really boring. It's only one particle. It has no interactions. You know, we keep making the same mistakes, so maybe we should think about whether this is correct or not. So, like I said, if dark matter doesn't interact with our stuff, but only interacts with itself, and what I'm calling self-interacting dark matter, you know, the only way we can find out about it is through gravity, but its gravitational effects would be different, because structure would be different because of its own interactions. So we're going to look for, so the conventional ways of looking for WIMPs will not apply. In the case of it has dark light, that is to say light only in the dark sector, it's not interacting with us, but we can still look for interactions. And so this is work with, I did with Sheikh Agrawal, Francis Saracine, and Jacob Schultz. And we asked the question, could you have darkly charged dark matter? Now, you might think, well, it's not interacting with dark matter, so it's entirely unconstrained. But that's not true. Because if it does have its own interactions, we'd still know about it, potentially. And at the time we started doing this, there were a few constraints that people really emphasized. One was the ellipticity of halos. So although I said that dark matter is in a spherical halo, it actually has some triaxial structure. And if it interacted too much, the idea was that if dark matter interacted too much, that structure would be erased. Another thing is these bullet cluster type constraints. If dark matter interacted a lot, it would be like the gas. It would get stuck in the middle. It wouldn't go through the way those nice blue regions showed you that in that picture I showed earlier. Another thing is the survival of dwarf galaxies in halos. A galaxy can actually have not just stars rotating in it, but actually smaller galaxies. And so both the small galaxy and our galaxy would contain dark matter. And the idea is that if it interacted too much, that could lead to the evaporation of this dwarf galaxy, so we never see it. And it seemed to significantly impinge on the parameter space. So basically, with the collaborators I just mentioned, we asked the question, how reliable are all these constraints? And it turns out, although I think ultimately there'll be really interesting ways to look for this type of dark matter, when we did detailed analyses, we found that almost all the constraints were too strong or even completely unreliable. So we still don't actually know the answer. And part of it has to do with the fact that it's really hard to calculate some of these things. And part of it has to do with the fact that some of these things are distribution things. You can actually have some of the dark matter get stuck in the middle if the bullet cluster, because we don't know what the distribution was that we started with of dark matter versus ordinary matter. So in the clusters that were emerging. The survival of dwarf galaxies, it turns out that there's a lot of interactions internal to the dwarf galaxy itself that can swamp some of the interactions with the external environment. So because of the public lecture, I'm not going to go through all the details, but I will just flash something to say that it really is a lot harder to calculate these things in detail than the naive thing said. And when we did it very carefully, the bound changed a lot. And in fact, this bound is actually too strong because it was based on just trying to assume that ellipticity disappeared the way it was said in the literature, but it's actually a very subtle thing. So again, because it's a public lecture, I'm not going to go through it. But what I will say is that darkly charged dark matter is viable. You can actually have particles of mass of the weak scale charged as much as almost the electromagnetism scale, and it's perfectly okay, at least as far as we know. That's not to say if we do simulations, if we do more careful calculations, we won't be able to rule it out. But the constraints are much weaker than people had said in the literature. So there really is this exciting possibility that dark matter has its own world of interactions, and that conceivably we can detect them. But that's not all we did. I also did some work with Gigi Fenn, Andre Katz, and Matt Rees, where we considered the possibility that there's a rich structure of dark matter. So it's not all charged, only a component is charged. So maybe there's some neutral component, and some charge component. So maybe there's just not just one non-interacting dark matter particle, but there's dark matter with its own force, but it's not all the dark matter. Now you might say, why would I care about a small fraction of the dark matter? I haven't even seen most of it. But if you think about it for a minute, you'd say, why would I care about ordinary matter? After all, there's only 1/6 of the energy in ordinary matter as there is of all the matter in the universe. And the reason we care about it is precisely because ordinary matter has all these interesting interactions. And so the hope is that if dark matter also has such interactions, we might be able to learn about that component even sooner than we learn about the rest. And in particular, if there are interactions, it can be relevant for structure. So the simple double disk dark matter model, and we'll see in a moment why we call it double disk dark matter, is just that there's a dark photon with its own charge, a dark proton, and a dark electron. So it's very similar to what we have in the standard model, except it's all in the dark sector. Now, is this the only model? No, but it's probably the simplest model. And our idea was just to start with a simple model, and you can always complicate things. And so just like ordinary matter, it's going to radiate and cool and bind into atoms. And it would collapse into a disk, just the same way ordinary matter does, because it can radiate as well, because there's a dark photon. And not only could there be a dark matter disk, but it turns out it could be much denser than the ordinary disk, and that can have significant implications. In particular, it means that it's something that we can hope to see, because it would affect the velocity distribution near the galactic plane. So you can have rich signals because it's in the disk and it's so dense. And it turns out that, it was really a fun project for us because we're not astronomers fundamentally, but it meant we had to rethink all of the basics of astronomy in light of if these interactions actually existed. So I call it double disk dark matter. It's a little bit hard to see here, but in addition to the Milky Way disk, the idea is that there's a dark matter disk precisely because there's a component of dark matter that can radiate. That doesn't mean we don't still have the spherical halo, because remember, this was only a fraction of the dark matter. So there's a dark matter disk inside the Milky Way disk and the ordinary spherical halo. Now, I told you it affects the motions of stars, and this is really exciting because there's something called the Gaia satellite, which is measuring precisely the kind of thing I just talked about, measuring the position and velocities of stars in our galaxy. But it turns out it's a complicated business because you have to know that you have an equilibrium distribution of stars, or else all bets are off. And as I'm going to argue, people have done beautiful analyses trying to look at Gaia and figuring out whether or not this dark disk is constrained. But it's really hard. And a couple of the studies seem to provide strong constraints, but they also give somewhat contradictory results in terms of where the equilibrium position is. And there's actually another paper that I don't even mention here that does establish a dark matter disk, but with smaller density than we typically talk about. This bound for structure is something that I reworked with Eric Kramer. It was originally done by Flynn and Holmberg, but the idea is to measure the gravitational potential in and out of the plane of the galaxy. And then you use that to get a dynamical estimate of how much mass there is, and then by knowing how much ordinary stuff, when I say baryons, I mean ordinary stuff, then you can figure out how much dark matter there is. And it turns out we found the disk was allowed, but more recent work using the Gaia data was done by these two groups that are listed there. And they do get more powerful constraints if it's in equilibrium. However, there's a strong piece of evidence that tells me they might not be in equilibrium because they all measure different heights for the sun. And I don't know if you can read this table, but if you actually look at, basically for each different population of stars, you get a slightly different, you get a somewhat different result. And you also get a different height of the sun, which means we don't really know where this disk is, and we don't know if it's in equilibrium, because that would explain why you'd see different heights depending on your stellar population. So it's really interesting in principle, but we don't yet know the answer. And people have tried to use more data and put it together. And when they did that, they actually did find some constraint, but it's very sensitive. And it turns out this analysis, unfortunately, is harder to do reliably than we thought. But the general lesson that we do learn from here, and as a public lecture, I think it's important to see some general lessons, is that there really is a role for particle physics in astronomy. Because when we first did our project, we were told basically the dark matter disk is not allowed. And that was because people had fit things without thinking about the dark matter disk. But as particle physicists, we actually want to put constraints on what the new physics is or discover it. So the fact that you don't need it doesn't mean it's ruled out. It just means we don't yet know if it's there and how much of it there is. So there can always be an arbitrarily small density in a dark matter disk, and we would still not be able to find it. But for any given density, we should be able to look for it. But it turns out it really is important to have a model in this case. If you didn't have a model, you wouldn't be able to self-consistently do the analysis because one gravitational component affects another one. And then you have to consistently count for things. So in addition, there's just big messy data sets. So without a model, you're never going to find something. So I'm going to leave it at that. So I'd say the dark disk is still in play. But are there other ways to look? I'm just going to flash you a couple of other possible consequences. One thing that I studied with the student Linda Hugh was whether dwarf galaxies were oblate or prolate, because only oblate would be consistent with a disk. It's hard to do because we only measure sort of two-dimensional projections of the velocities, but you can look at correlations with surface brightness and velocity dispersion. I realize for those of you in the public, this is detailed stuff that you don't necessarily want to think about, but it is important, and there's also work doing with Sasha Brennenberger. And this is just to say, if you have large mass to light ratio, it turns out it doesn't agree with simulations, which tell you it's prolate, which could be tantalizing evidence, or it could just tell us that we have to do more simulations. But this is the kind of thing that we as particle physicists or astronomers have to do. Try to do simulations, look at the data, and see if there's some consistency between them or not. And if there's not, we get excited because it means there's something new. Another thing we looked at was the satellites of the Andromeda galaxy. It turns out, if you look at the Andromeda galaxy, remember I said there were these dwarf galaxies? Turns out about half of them are in a big disk. It's wide and it's large, but it's hard to explain because if in ordinary dark matter models, you'd expect it to be isotropic. And so the proposed explanations involve tidal forces when things merge together, but which would be fine except for the fact that they seem to have a lot of dark matter in them, which wouldn't happen if it was just the planes of the galaxy in ordinary models. So again, it turns out there's evidence that there could be dark matter in the disk. And moreover, that dark matter seems to be slower, and that's why it gets trapped, and that would be consistent with this thin, dense, dark disk we talk about. And the final, somewhat crazy idea, but it's fun to think about, has to do with meteoroid periodicity. So let me just take a few minutes to tell you about this wacky idea, which probably doesn't have anything to do with reality, but it certainly taught us a lot, and it might have something to do with reality. So it turns out you can go to the web and find every meteor that's hit the Earth and left a crater. So you could go to the Earth Impact Database and find all the craters, the size, and their age. And it turns out there's somewhere between 20 and 25 that are bigger than about 20 kilometers in circumference that have hit in the last 250 million years. That's really big. It means that the thing that hit was at least a kilometer big. So these are big impacts. So there's lots of impacts that happen all the time, but big ones happen very rarely. It's something like 30 to 35 million years periodicity. Now the question is it periodic or is it random? And this has been a big debate in the geology community. In fact, they got really mad at us for even thinking about this question. But it turns out there is some evidence that could be periodic. And if you have, again, if you have a model, you can make this into a truly scientific question. This is work I did with Matt Reese. So we assume there's a dark disk, and we ask whether there does seem to be some periodicity in the structure. Now, you might say, why would dark matter have anything to do with the periodicity? Why do I care? And I'm going to get to that, but I'm first going to just remind you what our galaxy looks like, which is that there's all the stuff that you usually think about, but then out there, tens of thousands or thousands of times farther away than the Earth is something called the OORT cloud, which you probably don't think about a lot. But it turns out the OORT cloud, which is really far away, is the source of long period comets, comets with periods bigger than 200 years. And it's so far away that stuff in the OORT cloud is very weakly bound to the sun. Because remember, the force of gravity goes like 1/distance squared, and this is thousands of times farther away. So the fact that it's so weakly bound means that if there's a small kick, it could basically kick it out of the solar system, or it could come hurtling towards Earth. So the notion is that every time you get a small kick, you're more likely to get a meteorite impact. And in our case, we say you're more likely to get a small kick when you are crossing a dense dark matter disk. And the idea is that when the solar system goes around the galaxy, it doesn't just orbit around, but it actually goes, it's about 250 million years to go around. But as it does so, it goes up and down like horses on a carousel a little bit. And the idea is that every time it would cross that disk, maybe there's more possibility that you would get this meteorite strike. So we looked at the evidence, we looked at the periodicity, and we found there was some evidence for it. And moreover, it looked like it crossed at about the right time to explain the last major mass extinction, which happened about 66 million years ago and was responsible for the extinction of the dinosaurs and basically 2/3 of the rest of the species on Earth. It was a big extinction. And actually the story, I described it in my book, the story of how they figured out that it was connected with an impact. It's an incredibly interesting story. It's a great scientific story. How you could tell that it was something that was associated with something from space and not just something internal to Earth. And that has to do with something, it has to do with this layer of clay that separates between white rock and gray rock. And here I actually had the opportunity in Spain to see this. So you don't actually see the rock very well, but we were looking at this layer. That was part of the clue that explained ultimately that it was some meteorite impact. It was pretty interesting. And that's what the place looks like, in case that wasn't enough reason to be there. Really beautiful. So this is just to say there's lots of consequences. We're talking about this really abstract stuff, but it turns out that all the abstract stuff, I mean, it was really fun to think about it, is, you know, a lot of it is connected to the world that we were living in. And it could be that there's this connection, but whether or not there is, we learn a lot by studying astronomy and studying particle physics of what things are made of. And you even understand the basic structures of life in terms of these elementary processes. So I don't know if the dark disk is right, but the search for it is ongoing as we speak. But there are these amazing connections in the universe. So that's the book. I like the cover because it has this comet going through. And this is the slide I'm just going to end with because it's just kind of funny. Because I had some friends who wrote for the Big Bang Theory. And so when I was, I visited the set one day and they said, well, why don't you just be an extra? You can just, and it turns out I'm a much better actor than I thought because I was supposed to sit in the cafeteria and look inconspicuous. And it was so inconspicuous that no one realized I was there, even though I'm like right behind them. And so this is what I like to use as my analogy from why we build models, because there's a lot of things that could be right in front of our eyes that we won't see unless we know to look for them. And it's really important to know what you're looking for. Because once I tell you I'm there, it's pretty easy to find me. And the same way, if we know what we're looking for in particle physics or in astronomy or in dark matter, we hope we'll find it. So thank you for listening.
Thank you very much, Lisa, for this beautiful talk. And we will have now time for questions. And as I mentioned at the beginning, the way we would like to do this is that if you have a question, please raise your hand and then I will call on you.
This is really strange for me, by the way, because first of all, you didn't applaud. And second of all, I have no idea how many of you have questions, and I have no idea what your questions are.
Okay.
So please make it easy for me.
I'm gonna unmute Alison Silva for the first question.
Hi, thank you, Professor Randall, for the excellent lecture. So my question deals with an open problem in geophysics called Chandler's wobble. I don't know if you're aware of that, but the Earth's precession period is longer than expected, and the reason is believed to lie in deformations inside the Earth, but the source is unknown. I wanted to know if dark matter could account for that.
Yeah,
I guess the bigger question is...
So there's lots of different effects in geology, which was fun to learn about. But the time scale is very different in that effect, I think. So the time scale is quite different. So I don't think so.
I guess the bigger question is really, shouldn't we expect dark matter to clump during planet formation, forming halos more or less the same way as it does around galaxies, and that this halo
actually, the answer to that is no, because so a lot of the stuff, so there's sort of, you can ask like why stars form and things like that. A lot of that has to do with all the other interactions. So you need a way to dissipate energy in order to collapse more. So to get into those smaller structures, you would need a lot more interactions than even in these models. Because basically the dark matter is just going back and forth, it's just bound by gravity. Whereas other stuff is atomic forces, it's molecular things, there's other ways of cooling.
Okay, thank you. I have
somebody needs to mute because there's some weird noises coming in.
I think everybody is muted. I have a question in the chat from Robert Cooper. Question is, if we can observe the effect of dark matter, example lensing, the increased speed of material in the galaxies, what are the observed effects of dark matter near black holes?
So, I mean, so the question is there enough stuff to lens it? So basically, if there's enough matter, but you know, when I wrote that down before, you know, it was like I had a galaxy there. An individual black hole, even though it's quite massive, is probably not massive enough to bend it significantly enough that we can see it. In principle, it could bend light around it. And now, if dark matter has interactions, it could even dissipate and fall into a black hole. But it would be a very tough way to find black holes using dark matter.
Any other questions for Lisa?
I know it's weird, but remember, it's weird for me too. So if you have questions, feel free to ask.
Right, let me see. I don't see any other hands.
Is that a hand?
Okay.
Hello.
Oh, yes. Okay. Stephen Harris, please go ahead. You're muted now. Can you unmute yourself?
Okay, could you hear me?
Yes, now it's good.
If gravitational wave detectors could be improved, just for the moment, let me talk about near infinite sensitivity. To what extent would that let you look at what you called dark photons, which I interpret to be an interaction of dark with dark matter? But the primary question is, to what extent can such improvement in gravitational wave detectors give you further information to really map out dark matter in detail? I think that's far enough. Okay.
Thank you.
Yeah, so I've actually done some work on gravity wave detection. And I was originally motivated by trying to learn about dark matter. So I can't tell you if it's like infinitely precise, but I can tell you if it's as precise as it is. It's really very, very hard to do, because you need big, massive, I mean, basically, you know, it can detect big, massive events. It's just a lot of, you know, so the stuff that really clumps to small sizes is kind of ordinary matter because of all the other interactions.
My question was one of principle. I understand the difficulties in just if it existed by some mechanism we're not now practicing, I'm just interested if that would allow a mapping of the dark matter distribution and in turn with what you call dark photons.
Well, I have to admit, I'm kind of afraid to say anything because it's not actually a question I've thought about. It'd be really hard because you'd have to get enough quadrupole radiation from dark matter somehow. And so first of all, have to have some sort of asymmetric structure. So if you can really sensitively do it, I mean, when they measure the collisions of black holes, at least so they can perhaps measure the collision of the entire galaxies. If they could really measure everything, in principle, but it's so far, it really is such an in principle question. It's so far from the way things actually would work that it's just not something I've really thought about in detail.
Thank you.
Okay. There's one more question in the chat from Claire Yu. She's asking, what is the density of dark matter?
It's about, what is it? GeV per centimeter cubed. I mean, it's just what it is.
Okay, maybe time for one more question if anybody. Arthur Thompson, please go ahead. Sorry, I think
yes.
Oh, it's good. Go ahead.
Yes, in that bullet cluster, how did they generate the pink and blue clouds?
Yeah, that's a good question. But you notice I very cleverly gave you that slide after I gave you the slide on gravitational lensing. And they actually used gravitational lensing to figure out that there was stuff there.
So this is just artificial coloring based upon
the color is
what
just
you were guessing.
so that you can see it. The color is not real. Yeah.
Okay. Very pretty though.
It also makes it easier to see when you're giving a lecture. I've tried in black and white. Very hard to see.
All right. So thank you so much for everybody for the attendance, and in particular for Lisa for this wonderful talk. And we hope to see you again next week at the same time at the next public lecture. Thank you very much. Bye-bye.
Good night, all.